If the spin directions of free electrons can be aligned, the following phenomena can occur. Generation of magnetic moment. Electrons possess a magnetic moment due to their spin. When the spin directions are the same, the magnetic moments of the electrons align in the same direction. Therefore, aligning the spin directions of free electrons results in the alignment of their magnetic moments. Generation of magnetic force. Magnetic moments generate a magnetic field. Aligning the spin directions of free electrons causes their magnetic moments to align, resulting in the generation of a magnetic field. This magnetic field interacts among the free electrons, creating forces that attract or repel the electrons. Formation of ferromagnetism. When the spin directions of free electrons are the same, they experience an attractive force and naturally combine. This type of bonding is known as ferromagnetic coupling. Electrons bound by ferromagnetic coupling act as a single magnetic entity. Ferromagnetism is a property observed in elements such as iron, nickel, cobalt, etc. These elements exhibit ferromagnetism because the spin directions of free electrons can easily align. In reality, achieving alignment of the spin directions of free electrons is challenging. Free electrons move at high speeds, making it difficult to change their spin directions. However, recent developments in utilizing quantum mechanical effects have led to the development of technologies capable of manipulating the spin directions of free electrons. With advancements in such technologies, there is an expectation of creating new forms of magnetic materials or semiconductors. If the spin directions of free electrons can be aligned, these electrons will form magnetic dipole moments, generated by the alignment of charges and the rotation of charges, resulting in a magnetic field. When the spin directions of free electrons are the same, these electrons collectively generate a magnetic field in the same direction. This magnetic field induces attractive forces among the electrons, causing them to bond together. Through this phenomenon, when the spin directions of free electrons are aligned, the electrons exhibit magnetism. In other words, aligning the spin directions of free electrons causes them to act like magnets. Various methods can be employed to align the spin directions of free electrons, including applying an external magnetic field. Applying an external magnetic field aligns the spin directions of free electrons in the direction of the external magnetic field. Applying an electric field. Applying an electric field aligns the spin directions of free electrons in the opposite direction to the electric field. Using laser technology. Laser light can be used to change the spin directions of free electrons by providing them with energy. Aligning the spin directions of free electrons has applications in various fields. For example, it can be applied to increase the storage capacity of computer hard drives or develop new types of magnets. If the spin directions of free electrons are aligned in a state where they are not bound to any material but are freely moving, several phenomena can occur. Generation of a magnetic field. The spin of electrons results in a magnetic moment. When the spin directions are the same, a magnetic field is generated in the same direction. 2. Ease of bonding with atoms. Electrons with the same spin directions experience attractive forces, making it easy for them to bond with atoms. 3. Potential for signal transmission. Magnetic moments can generate electromagnetic waves, so aligning the spin directions of free electrons can be used to transmit signals. Although these phenomena have not been experimentally confirmed yet, they are theoretically plausible. Methods to align the spin directions of free electrons include using an external magnetic field. External magnetic fields play a role in aligning the spin directions of electrons. Utilizing lasers. Lasers can provide energy to free electrons, allowing for the manipulation of spin directions. If the alignment of spin directions of free electrons can be achieved, it holds promise for applications in new technological developments. In an empty space, free electrons with aligned spin directions can collide and bond together. When the spin directions of free electrons are the same, these electrons collectively generate a magnetic field in the same direction. This magnetic field induces attractive forces among the electrons, causing them to bond together. To achieve aligned spin directions of free electrons in empty space, the most common method is to apply an external magnetic field. When an external magnetic field is applied, the spin directions of free electrons align in the direction of the external magnetic field. Therefore, by applying a sufficiently strong external magnetic field, the spin directions of free electrons can be made uniform. When the spin directions of free electrons are aligned, these electrons bond together to form magnetic dipole moments. These magnetic dipole moments induce attractive forces among the electrons, leading to their bonding. Through this phenomenon, when the spin directions of free electrons are aligned in empty space, the electrons exhibit magnetism. In other words, aligning the spin directions of free electrons causes them to act like magnets. In practice, research is underway to align the spin directions of free electrons in empty space to create bonded structures of free electrons. This research is expected to have applications in the development of new types of magnets or optical devices. However, achieving complete alignment of spin directions of free electrons in empty space is challenging. Free electrons are constantly in motion, making it difficult to maintain a consistent spin direction. Therefore, to align the spin directions of free electrons, it is necessary to continuously apply an external magnetic field,